Hello, my name is Hui Kunbi, and I am an assistant professor at the Institute of Computing Technology, Chinese Academy of Sciences. In this video, I will briefly introduce our work using first-person view for pedestrian trajectory prediction. State-of-the-art methods use either real-time top-down view images or real-time first-person view images to predict pedestrians' trajectories for robotic navigation, autonomous driving, etc. Many prior works chose to use top-down view images due to it is easy to access. For example, they can be captured by surveillance cameras and shared between pedestrians. However, due to pixel precision, it provides limited dynamic scenes context. The latest studies use the first-person view images that can provide detailed dynamic scenes context, like eagle motion, to predict pedestrian trajectories. For applications like robotic navigation, where each robot equips an onboard camera, first-person view images are easy to access. For other scenarios, it might require to install at least a camera per pedestrian, which motivates us to create an in-house simulator to overcome these limitations. For the first time, we propose to use simulated first-person view images to introduce detailed dynamic scenes contexts, like eagle motions, which requires no physical equipment. Therefore, our study can be applied to any application without additional cost. We named our in-house built first-person view simulator as FvSim. Given the observed ground-level 2D trajectory for each pedestrian, FvSim uses Unity to generate a dynamic virtual environment with the camera settings that are shown in the upper right figure and renders the corresponding first-person view images for each pedestrian. This video shows the first-person view images for each of the 4 pedestrians based on their own observed trajectories. Using the simulated first-person view images and observed 2D trajectories as input, we proposed our deep learning model named Future to predict future 2D trajectories. As shown in the Future's pipeline, there are 5 major modules, including 2 encoders, one for observed pedestrians' trajectories and the other for first-person view images, followed up by 2 modules, social aware attention module and view aware attention module, and finally connected to the trajectory decoder. We use multi-head attention mechanisms for both social aware attention module and view aware attention module to capture social interactions and visual features, respectively. To evaluate our final model Future, we use the most common evaluation metrics, average displacement error and final displacement error, to compare Future to these listed baseline models. We then performed an evaluation study using various control settings to evaluate the contribution of each major component of Future. The results are shown in the table. For each dataset, we have highlighted the model with the best performance among all 8 models, including ours. As we can see, our model Future outperformed the others, especially for dataset ETH, hotel, and university. The right figure shows the effect of the variety loss. Less change with respect to the number of sampling k means better generalization. It showed our model is more generalized. Although for dataset 01 and 02, our model does not perform as good as other baselines, which leads us to further improve our model in the future study. To better evaluate Future, we first visualized the predict trajectories and the corresponding ground truths in the first row of figures. The first figures demonstrated the scenarios like meeting, following, and avoiding. The predict trajectories and their ground truths are overlapping for most of the showed cases. Due to the multimodality, the predict trajectories sometimes do not agree to the ground truths. Comparing to ground truths, our predict trajectories seem to be more conservative, especially in meeting scenes, to avoid potential and future collisions, which is of particular interest for some specific applications due to safety concerns. We then realized the predict trajectory distribution in meeting and following scenes shown in the second row of figures. We observed that the pedestrian collision is unlikely to occur because there is no overlapping among the predict trajectory distributions at any step. and the variance of the distribution is reduced with the increased probability of collisions occurring between pedestrians. This shows that the future can well capture the fundamental factors, including multimodality, social interactions, and sense contexts. Last but not least, we realized the learned attention weights from social aware attention module. We observe that the focused pedestrians will pay more attention to the pedestrians who are nearby or attempt to move towards themselves. This shows the social aware attention module can well capture spatial and temporal social interactions. We quantitatively and qualitatively evaluated the contribution of the first-person view information in the pedestrian trajectory prediction task. First, we found that adding first-person view information to future leads to a decrease of 9.8% and 10.6% for average displacement error and final displacement error respectively. This means that the model's performance has been improved. Then we visualize the learned attention weights obtained in the view aware attention module. The figures show that the simulated first-person view images can well capture equal motions for the focused pedestrians. Equal motions such as the focused pedestrians' visual perspective effect on the neighbors and the moving intentions are important in trajectory prediction, but difficult to capture using top-down view images or social patterns learned from the numerical inputs. Overall, it shows the first-person view images do play an important role in pedestrian trajectory prediction. To conclude our work, we first developed a simulator FvSim to generate a 3D simulated scenario and render the first-person view images for each pedestrian. Then we built a first-person view-based trajectory prediction model Future to capture social interactions and visual features with equal motions by using multi-head attention mechanisms. Our experimental results show that our model achieves state-of-the-art performance. For more details of our work, please read our paper. Thanks for watching.